So my name is Nick. I'm the CEO and co-founder of Radar. And as Jay said, I'll be talking to you guys about our MongoDB implementation. So two big topics to cover today. One is what is Radar? I'll give you guys a demo and tell you a bit about what we're building. The second part is why and how do we use MongoDB? So let's start with what is Radar. So we call ourselves the location platform for mobile apps. And our mission is to help companies collect, analyze, and act on location data. Basically, if you're building an app and you want to know where your users are, we aim to make that really easy. My co-founder and I met at Foursquare back in 2012, so we've been thinking about location for a while. We launched a few months ago. We have a few hundred developers that have signed up, and they're using Radar to process millions of locations per day, so we're really excited about the traction that we're seeing so far. So why is location interesting? What is the opportunity here? The best apps are using location to build better products. So think about a couple examples. Starbucks is using location to power order ahead and show you places that are nearby. Foursquare, if you guys use Foursquare, is using location to know when you walk into a place and they'll serve you interesting content there. Uber is obviously using location to estimate arrival times, manage supply and demand. And if you think about apps like WeChat, you can, within a single app, look up a place to go to dinner, see how busy it is there, order a car to take you there, see it coming to you. When you walk into the restaurant, the menu will pop up. So great apps like these are using location in creative ways to increase revenue, increase engagement, improve operations. We feel like most apps will be doing this in the near future. The problem is this stuff is really still too hard to build. So take a seemingly simple example. Let's say we're building a travel app. And we want to send a push notification when a user lands at an airport in a new city. Seems like a relatively simple problem to solve. When you start to unpack it, you realize there's lots of moving pieces. So the first part is you need to build background location tracking on iOS and Android. There are cross-platform differences between the two platforms, which I'll talk about. You want to do this in an accurate way, but also in a battery-efficient way. Takes lots of trial and error to get this right. Second part is you need to acquire place data for geofences. So if you want to geofence airports or cities, you need to get that data, set it up, and that can take some time to do well. If you want to know if a user is traveling, some apps the user will tell you where they live, and so you can infer if they're traveling based on how far they are from home. But if not, you could potentially store sensor data history for the user and cluster it and learn where they live and where they work. But that takes some time to do well. And then all this stuff you need to test and maintain, right? So lots of trial and error to get this right. With every operating system release comes new features around location services, new limitations. Android O, for example, which is coming out in a few months, places all sorts of new interesting limitations on background location. Long story short, all this adds up to months of engineering time. If you want to do this well, it's just a total pain in the ass. And the same applies to other use cases as well. Not just travel apps, but social apps, dating apps, food apps, and on the enterprise side, on-demand apps and delivery apps. And if you think about other similar technical challenges, there are generally great full-stack solutions available to developers. So you think about payments, there's Stripe. You think about analytics, there's companies like Amplitude or Mixpanel. You think about crash reporting, you just pop in Fabric and turn on Crashlytics. The same really can't be said for location. There are tools out there, but they aren't truly great full-stack developer tools. And that's what we're trying to build with Radar. So our goal is to make location really simple. We want to let developers add location context and tracking to their apps with less than 10 lines of code. There's three different aspects to our product. The first is geofences. So geofences are regions or places that you want to monitor. We basically offer 10x better geofencing than what you can get out of the box with native solutions. I'll talk a lot more about that later on and how we use MongoDB to power a lot of that stuff. Second part of the product is what we call insights. Radar can, over time, learn where a user lives, where a user works. We can tell you if the user is currently at work or at home or traveling. We call that our insights product. And you can combine that with geofences, as I'll show you in a second. The third piece to our product, which is in private beta right now, but we're going to be launching relatively soon, we call places. And so without setting up any geofences, we can tell you with a certain degree of confidence which place a user is at. And we integrate with Facebook Places and Google Places to power that. So all this put together lets you do things like, let's say you want to check if a user is at an airport and traveling. This is basically the use case that we talked about before. 5 lines of code, you can call track once, get the user's current location, see if they're at a place, see if you have insights for the user, see if the place has the category of airport, see if they're traveling. That's it, you're done. Say you want to do something when a user visits a Starbucks in the background with stop detection. Again, you just pop the Android SDK in, set up your receiver, listen for events, see if the event is of the type place entry, and check to see if it's of the chain Starbucks. That's it. It's a couple lines of code. Say you want to set up a webhook that will listen for the user exiting their home. You just add a webhook in Radar, check the event type. You can pull the user ID from the event and do whatever you want with that. Or maybe you're building a delivery app and you want to dynamically create geofences whenever a delivery is scheduled. Again, you can just hit our API, pass in whatever metadata you want, and set up a geofence. So again, we're aiming to make location simple, let you power this stuff in a couple lines of code. And we're aiming to build a platform that kind of elegantly spans a bunch of different use cases across consumer and enterprise. So we talked about travel, but shopping apps, food apps, on-demand apps, whatever you want. I'll show you guys a really quick demo. You may notice the branding is slightly different in this slide deck than what you see on the site right now. I was hoping to get this rebranding live before I gave this talk, but it's not quite ready yet. You guys will see that in the next couple days. But basically, really quickly, this is the Radar dashboard that you would see if you're a developer using our platform. We show you how many users you're tracking per month and how many geofences are active per month. This is actually just a personal test org that my co-founder and I use quite a bit. You can see I've created a geofence for MongoDB HQ. It's probably unnecessarily large, but there it is. I can specify the metadata for the fence when I create it, like a tag, which is like a group ID, and what we call external ID, which is an ID that could map to something in your system. So the delivery use case we talked about, you might set tag to delivery, and you might set external ID to your delivery ID. But these can be circles or they can be polygons. So if I type in Soho, you can see I have a geofence for the neighborhood Soho. This is a polygon. It's tagged neighborhood. I can create geofences via the dashboard, via the API, or I can bulk import them from my own place database. Every user that you're tracking will show up in the dashboard as well. We have names and descriptions for the users, but you don't have to send us any PII. You just have to send us a stable, unique ID. This is actual real data for me, so I can click here. You can see my current location is that blue marker right there. We've also learned where I live and work just by unsupervised learning of my sensor data over time. And this is pretty good. I work at a co-working space called Workbench in Union Square. But we can learn this for any user over time and tell you the degree of confidence for that as well. And then finally, we send you a stream of events. So these are things like geofence entry events and geofence exit events, but also entered home, exited home, entered office, exited office. We can tell you if a user starts traveling, and we can also predict the user's place if you have that feature turned on. So here was my entry event to Mongo HQ. Again, I can set up a webhook and receive this server side, or I can receive this client side. I was doing a bunch of testing earlier with an Android phone and walked over to Barnes & Noble in Union Square. You can see this here. I can click and drill into the place details and see the categories of the place and what the chain is. And again, this is stuff that you can add to your apps in just a couple lines of code. So that's the super quick demo. Now let's talk about Mongo. So really two things that I wanted to dive into, and then we can do Q&A. The first thing is how we use geospatial queries and indexes to power a lot of the geospatial stuff that we do, and also why we chose Mongo for that. The second thing that I wanted to touch on is how Mongo is just a natural fit with a JavaScript-heavy stack. And before I jump into this section, just to give you guys an idea of what our stack does look like, this is a super simplified view, but up top you have different clients. You have our iOS and Android SDK that talk to our API. You have any API clients that customers build. It's a RESTful API. Everything is JSON. So JavaScript. Our web app is React, more JavaScript. Our API servers and workers, our node, more JavaScript. We use Mongoose, which is an ORM for interacting with Mongo in Node. And then MongoDB is our database for our application. There's some other stuff going on here, but that's what's relevant to what we're going to talk about today. So first, let's talk about geospatial queries and indexes. And you may be asking, like, why do this stuff on the server at all? There's some pretty robust geospatial capabilities on the client. You think about iOS, for example, they have a framework called region monitoring, which is geofencing. Android has something similar. So why even do this on the server at all? There are some limitations to what you can do client-side that we aim to overcome with our platform. So one of the limitations is iOS has a 20 geofence limit. Android has a 100 geofence limit. If you want to monitor more regions, you basically have to devise a system to swap geofences in and out as the user moves around. It's kind of a pain in the ass, but it's something you can do. On iOS, there's no notion of stop detection or dwell events. So on Android, you can listen for entries, dwells, and exits. On iOS, there's no notion of that. So iOS will tell you when a user enters a region, but they won't tell you if a user has stayed in a region for any amount of time. You can't monitor polygon geofences, just circle geofences. They're only accurate down to about 100 meters. And it's push, not pull. And what I mean by that is the operating system will push geofence entries and exits to you, but there's no easy way to say, hey, tell me which geofences the user is in right now. And so we chose to basically make our SDK really lightweight. It wakes up when the user starts moving around and sends lat longs to Radar. And we do all of our geofencing and event generation server-side using Mongo, which I'll talk to you about in a second. But this lets us bypass those geofence limits that we talked about. It lets us store the state for the user, whether that's what geofences they're in and when they entered them, or the user's location history, so that we can do stop detection and dwell events. We support circular and polygon geofences. It's as accurate as the device can report. So we take lat longs in with an accuracy sort of assigned by the device. And we can do geofences as small as 30 meters in practice based on what the device can give us. And it's push and pull, so we can diff the user's current geofences and the geofences they were in to get entry and exit events. We can also write geospatial queries to figure out which regions the user is in at any given time. So I'll show you what that looks like in a second. Just to sort of understand our schema first, we have three main objects in our system. Geofences, users, and events. This is a obviously super simplified view of our geofence schema, but each geofence document has an ID, and then it has a geometry, which is a polygon. For those of you who haven't used geospatial features in MongoDB before, this is Geo JSON format, so it's just sort of a standard format to express polygons or points in JSON format. Basically just an array which represents a ring of coordinates for the shape of the polygon. Users also have an ID. We represent their current location as a point. Also in GeoJSON, we store an array of the user's current geofences, so it's their geofence IDs. And we also store basically a list of, or a map of, the times at which the user entered each geofence. And this lets us do things like stop detection. And so this is a really natural way, I think, to express where a user is, what geofences they're currently in when they entered them. It's all in a single document. It doesn't need to be spread out across different tables. And you can use this in conjunction with geospatial query operators and geospatial indexes, which I'll talk about in a second. The last object is an event, which has an ID. It has a type, like user entered geofence. It maps to the user and geofence that the event corresponds to. And we also store the location for which the event was triggered. So the geospatial query operators that we use are near, which will basically return documents that are near the specified point or polygon. Within, which will return documents that are within the specified polygon. And intersects, which will return documents that intersect with the specified point or polygon. And you can use the geospatial index to make all of these super performant. So what does this actually look like in practice? Let's say we want to figure out which geofences the user is near. What you're looking at here, by the way, is JavaScript. So as I mentioned, we use Mongoose as our ORM, our layer for interacting with Mongo. The queries look similar, but you're basically calling find on our geofence model, and you're getting the error, if any, and an array of geofence documents out. We can say, hey, let's call find on our geofence model and say, let's find geofences near the user's location with a max distance of 10 kilometers. Super easy, super expressive. We can do something with that list of geofences for example, sync it down to the client to overcome some of those geofence limits that we talked about before. Let's say we want to find which geofences the user is in right now. Again, we just do a find on our geofence collection, and we look for geofences where the geometry intersects with the user's current location. Really straightforward, really expressive. Let's say we want to figure out if the user entered or exited any geofences. Same query. Because we're storing a list of the user's current geofences, we can basically do a diff and figure out which geofences the user has entered or exited. We can do some more advanced geospatial calculations if we want. We can do stop detection. But at the end of the day, it's just a super simple, expressive way to figure out which geofences the user is in and whether they've entered or exited any. And by designing the system this way, it lets us overcome all of the client-side limitations that we talked about. And we were able to get up and running with this very quickly. Want to just briefly touch on why MongoDB over PostGIS. For those of you who know PostGIS or who don't know, it's basically an extender on top of Postgres that adds geospatial features. We like the fact that geospatial features are built into MongoDB. It's not an extender. It's sort of a core part of what Mongo does and what Mongo is. We like that. A lot of the advanced features of PostGIS are just sort of overkill for our use cases, and I think for most sort of modern applications, the stuff that I highlighted in the previous few slides gives us what we need. It's really natural. It's easy to use. It's very expressive. And there's these two reasons. There's also everything in the next section that I'm about to talk about, which is just that Mongo is a really natural fit with a JavaScript-heavy stack. So again, our stack is an API where objects are JSON, a web app, which is React, it's JavaScript, API servers and workers, which are Node, it's JavaScript. Mongo represents documents in JSON/BSON, friendly with JavaScript. So what does this mean? It's a really natural way, using JSON is a really natural way to model users' geofences and events. I think it's sort of more natural than modeling them as rows in a relational database. As I'll show you in a second, transforming those documents to API responses requires minimal application logic. I'll show you what that looks like in practice in a second. Geospatial data is represented as Geo JSON throughout all parts of our stack. So in the database, in our application layer, and I'll explain how we manipulate that, and also in our API. We want developers working with geospatial data coming back from the Radar API to have a sort of standard format that they can easily plug into other systems. So Geo JSON is a great fit for that. And the cool thing is, as we think about growing our team, JavaScript developers can work across all parts of our stack. So obviously there's domain-specific knowledge when it comes to best practices for Mongo or React or whatever, but it's very familiar to folks regardless of what part of our stack they're working on. This is what it looks like to take a user document and transform it into an API response. The document in the database has an ID. It has an organization, which in our system represents the customer that the user corresponds to. It has a location. Basically, to send it out through the API, we pass it through a pipeline step and sanitize it. We change the IDs to strings. We remove the internal fields like organization, and that's it. So the way documents are stored in our database is actually very similar to the way they come back in the API. It's just easy to wrap your head around and keeps our application layer simple. I've shown you a bunch of GeoJSON already, but again, geospatial data is represented as GeoJSON in our database, in our application layer, in the API. Take a look. It's a really standard format, easy to understand, easy to use. And in our application layer and also on our web dashboard, we make use of GeoJSON heavily. So some great libraries for you guys to check out. One is Turf, which is put out by the folks at Mapbox. It's basically a JavaScript library for all sorts of geospatial calculations. They take GeoJSON data in, they spit GeoJSON data out, so it's very natural to just sort of plug everything together. We use Google Maps for visualizations in our dashboard. Part of the reason we chose Google Maps over Mapbox is just because they have great place data built into the maps, which helps our customers sort of orient themselves around the places that they're monitoring. But part of the Mapbox toolkit and something that we're sort of using separately with Google Maps is this library called Supercluster, which lets you do really performant client-side clustering of geospatial data. So this is a customer that, and this is actual real data from a customer that has about 50,000 users kind of in the Northeast, and we're able to use Supercluster again, with data that just comes out of the DB, out of the API, throw it into this framework, cluster it, display it on a map, never changes formats. It's always Geo JSON. So that's basically it. We'll do some Q&A, but just to recap, we covered what is Radar. Hopefully my description made sense. Why we use and love MongoDB, and in particular we highlighted how we use geospatial queries and indexes to do geofencing server-side, and why that's great, and how Mongo is a really natural fit with our stack, which is very JavaScript heavy. Hopefully that was clear and interesting, and that's it. Thank you, guys. Guess we have time for some Q&A, yeah? Yes, sir. Yeah, so the question is, do we encrypt information? Do we keep it? Yep, and I guess in general, just talking about privacy. So obviously, with location data, privacy is super important. I think I mentioned this during the presentation. I think one thing that's worth highlighting is we don't take any PII into our system, right? All you do is send us a stable user ID, and that's it. So if I were to, for example, impersonate a customer and log into their account, I could see a bunch of location data, but I wouldn't know who this person was necessarily, right? The answer is, yeah, we do encrypt it end-to-end. Our API is HTTPS. We store this in a smart way. It's not encrypted at rest, like the location data per se, but again, just to highlight no PII being sent, and privacy is super important to us. So hopefully that answers the question. Was there a second part to it? Yeah, so we do store historical data to do things like cluster it and figure out where a user lives or works. Again, it's anonymized, right? So it's not like we're storing the user's name or email address with this. It's all just sort of tied to that stable user ID that you give us. Does that answer the question? Cool. Yeah. So the question is, how do we throttle and reduce the noise, especially as our traffic grows? It's an interesting question from sort of an internal perspective, right? How do we build a system that scales and doesn't fall over if we're installed on tens of millions of devices someday, and hopefully we are in the near future. We also want to think about this in terms of the client-side implications of being on all the time and collecting a lot of data, right? So what's important is to do this in a battery-efficient way and not kill the user's phone by staying awake and using GPS all the time. So we try to be judicious with how we wake up the SDK, when we wake up the SDK, when we grab a lat long from location services, or when we do a Wi-Fi scan or a Bluetooth scan to get that ambient sensor data. We try to be really smart about waking up, getting it quickly, going back to sleep, and only grabbing it every minute or two, right? So it's not like we're getting constantly streamed data all the time from every single device. We're batching it, we're being smart about when we're collecting it. And we're also only collecting it when the user is moving around, right? So if the user is at the office or at home, or they're not walking around or driving around, the SDK just goes to sleep. Cool. Thank you, guys.
Thanks. Appreciate your time.
Yeah, thank you.
All right, guys. Thanks a lot for it.